Hi, my name is Tim and I'll be presenting our work on adaptive bootstrapping for self-distillation. The goal of this work is to pre-train an encoder in a fully self-supervised way such that the learned representations can easily be transferred to any downstream tasks. Most works achieve this by learning representations invariant to semantic preserving data augmentations. The stronger the augmentations, the better the representations are. However, making them too strong makes them lose their semantic preserving nature. In this case, you cannot recognize the dog anymore if the Gaussian blur is too strong. If we had access to an oracle indicating valid positive pairs, we could simply apply a coherence loss between such positive pairs. Instead of learning data augmentation invariant features, we would learn features invariant to intra-class variance. Since we don't have access to such oracle, we can approximate it by using the structure of the learned latent space. This brings us to the first section on image-level bootstrapping. As a proxy for the oracle, we can use pairs of nearest neighbors in the latent space. A coherence loss can be applied between an augmentation of an input image and the nearest neighbor of another augmentation. This has been shown to be successful in a contrastive learning setting. We would like to leverage such nearest neighbor bootstrapping scheme in a self-distillation setting. There are non-trivial differences between the two learning paradigms. Most notably, contrastive learning uses explicit pairs of negatives, which self-distillation does not. This makes self-distillation particularly unstable and prone to collapse. However, self-distillation methods do show state-of-the-art performance due to not having explicit negatives, which can sometimes be wrong. Empirically, we observed that self-distillation and image-level bootstrapping does not work out of the box, as self-distillation is much less robust than contrastive learning. However, image-level bootstrapping can be improved following two aspects. The first one is that valuable self-supervisory signal is discarded. Indeed, explicit invariance to data augmentations is not enforced. To overcome this issue, we propose probabilistic nearest neighbor retrieval. And secondly, the effectiveness of using distance metrics in the latent space as a proxy for semantic closeness is contingent on its quality. That means that bootstrap positive pairs are not necessarily good, especially at the beginning of the pre-training when they are mostly based on low-level features. To overcome this issue, we propose what we call adaptive bootstrapping. Instead of systematically bootstrapping neighbors, we define a conditional sampling distribution proportional to feature similarity. The more similar an image xj is to the query image xi, the most likely it will be used as a positive pair. To form a positive pair, we can simply use an augmentation of the query image xi and an augmentation of a sampled image from the distribution xj star. It follows that there is a non-zero probability of sampling xi from the conditional distribution, which leads to an explicit learning of data invariant features. Visually, this is how the sampling distribution looks like. In the first column, we have the query image, and on the right side, we have the elements in the conditional distribution, where the green bar denotes how probable it is to sample such image. Since the bootstrapping is contingent on the quality of the latent space, we probe the latter with a semantic closeness condition and bootstrap accordingly. Intuitively, this condition boils down to check if two augmentations of the same input image are nearest neighbors or not. This condition cannot be satisfied with low-level features. This can be checked if the query image xi is the most probability in the conditional distribution. If it is, we sample another image xj star from this distribution to form a positive pair. If it is not, we use two augmentations of the query image xi. I will quickly finish with some results. We observe that our method outperforms the baseline on ImageNet downstream classification as well as few-shot transfer. In conclusion, we propose an adaptive bootstrapping method which is compatible with self-distillation. It stabilizes the training, avoids collapse, and improves the performance of the baselines. Thanks for listening and see you at the poster.